Why in evolution did we at all develop two eyes? Now, this is probably the question that was asked centuries ago. However, nevertheless, this remains to be the most fascinating questions of all times. A very good afternoon to one and all. Today, my center of focus would be related to this binocularity, otherwise called as binocular summation. So I would break this long title that is there into two. One, first explaining what is binocular summation itself. So what is binocular summation? In a very simpler terms to put binocular summation, imagine we are having two signals, or for instance, your right eye and the left eye. Now, what happens when these two signal inputs are simultaneously projected? Are we going to average it? Are we going to perform better with two eyes or not? And that quantification is given by binocular summation ratio. For a more comparisons, if I ask any visual function that we measure, right, say a spatial contrast sensitivity function in one hand, and on the other hand, the temporal contrast sensitivity function, we can clearly see that a monocular performance and the binocular performance do vary in both the domains. Now, the difference is that in the spatial domain, we know that the quantification that is there, that is, we know it's 41% of times always better binocularly than monocular viewing. On the other hand, in the temporal domain, we do not have such value or a quantification that could say how much are we performing binocularly. The second part of the study is interocular difference. Now, interocular difference is a very straightforward term. It is simply the difference between your right eye and the left eye. It can be your threshold difference, it can be your sensitivity difference, or it can be your visual acuity difference, right? So, Pardhan et al. In the year 1990, she had introduced these differences in front of one eye, using the neutral density filters and cutting the retinal illuminance and measuring what's the summation ratio. So, in this case, the intraocular difference is the retinal illuminance that's there. So overall, yes, absolutely, there are many studies that are there, especially in the spatial domain, to estimate these summation ratios. However, in the temporal domain, there are very few studies that give these values, and those studies have a huge variation in itself. So the main lacunae for the study was, the main lacunae that we found from all these analyses was that the summation ratio in the temporal domain is not very clear. So the first aim of the study that we had conducted earlier last year was to find what is the summation ratio in the temporal domain. And what we found as a part of the result was that, as I was talking about this interocular difference, when there is a greater difference, these summation ratios tend to be little lower, or in many cases, they started inhibiting the signals. Now, that is very interesting. It's interesting because the subjects that we had included in the previous study were all normals. Now, in these normals, somehow there was a difference between both the eye in terms of thresholds, and hence the summation ratio reduced. So that brings to the rationale of the present study, where we deliberately create such differences to find what's the summation ratio. So the other important questions that were asked in the present study was, how is the monocular and binocular modulation thresholds going to vary with retinal illuminance? And second, to estimate the summation ratios with interocular differences. So the two important outcome variables of the study are flicker modulation threshold itself and the binocular summation ratio. How did we go about it? We had used the advanced vision and optometry tests AWOT, and we used the Flicker Plus program where the observer is made to sit 1 meter away from the target, and the target appeared in 5 different locations, and the subject has to respond where they exactly saw the target using the response box. The interocular difference, however, was created using a neutral density filter turret that was placed in front of one of the eye of the subject and asked them to perform the same test. The target was shown in 5 locations, center and the 4 quadrants, and the target is a very low spatial frequency target with 15 Hertz temporal frequency. It was an adaptive staircase procedure where average of 6 reversals were taken as a threshold value for each of the subject. So the protocol, the stimulus parameters that were used were all well under control. All their characteristics were under control. We had used 8 neutral density filters that had created an interocular difference of 10% to 80%. And we had measured their binocular and monocular thresholds and then estimated their BSR values. Now, each of these 8 subjects, the normal subjects, had 3 sessions. One is having the neutral density filter in front of right eye and covering the other eye, and then the filter in the left eye and covering the right eye, and with both eyes open and the filter being placed in one of the eye. So this way we had collected the modulation threshold for 8 normal subjects, and I'm going to show the results of that. So the first question, first come first, the monocular and binocular modulation threshold, we want to know how it varied. So if you see over here, I'm going to focus on the monocular thresholds for the first time and how it varies as a function of retinal illuminance. Now I have classified this as center and quadrants. So center and quadrants is because of the stimulus location that we had used. So if you see, gradually the modulation thresholds tend to increase as the retinal illuminance decrease, and this was same for both center and quadrants. However, the center flicker modulation thresholds were far better than the quadrant flicker modulation thresholds. And when it comes to binocular, again, center and quadrant showed akin features of the monocular flicker modulation thresholds, but here as a function of interocular difference, because binocularly you have the filter in front of one eye and you're creating that difference, and hence the intraocular difference in the x-axis. And the critical point to note in both binocular and monocular flicker modulation threshold is that up to a certain point there isn't any major change that is happening in the modulation threshold. However, beyond a point there is an increase in the flicker modulation threshold both in the monocular and binocular aspect of it. To quickly summarize the flicker modulation threshold outcome variable, yes, there was a significant change up beyond a certain limit that is greater than 460 trollins of intraocular difference, and the center and quadrant had similar pattern. The binocular flicker modulation thresholds were higher or better than the monocular flicker modulation thresholds. So the other important question, the next outcome variable was BSR. What happens to the binocular summation ratio with a difference? Now, as a function of interocular difference, how did this BSR vary? Now, again, center and quadrant over here, if you see again from 0 to 40%, there isn't any change. There is a change, but there isn't any pattern that is coming out. But beyond 40%, there is a greater decline in the summation ratios, and there is inhibition also that is happening over here, and that was statistically significant as well. So the BSR showed again a trend that changed beyond the 460 trollins of intraocular difference. So to summarize the findings from the BSR, the summation ratios were absolutely greater than unity, and BSR reduced beyond 460 trollins, and the center and quadrants had similar patterns. So this is about interocular differences creating a change in the BSR and the FMT. Now one would ask, so okay, if there is an interocular difference or difference between both, yes, of course we would expect a difference. We came to know that, but what happens when there is an overall change in the luminance itself, right? Say for instance, from a photopic to a mesopic level. So that question was tagged along with the result of the previous outcome variable. So what we had done was we had used a different luminance, background luminance, that is from 10 to 40 candela per meter squared, and measured the modulation thresholds of 10 other subjects and estimated the summation ratios for those 10 subjects. And what interestingly came out was that the summation ratios did not change. Again, they did not show any variation in the patterns. They were all the same. There was no inhibition at 10 candela per meter squared. This tells us that the visual system is extremely sensitive, or in other words, it's very immune to minor changes that are happening. But beyond the threshold level, say beyond 460 trollins, there is an absolute decline in the summation ratios, or the visual system loses its sensitivity and becomes very insensitive for the changes that is happening. So to conclude with the monocular thresholds, they did change, both monocular and binocular thresholds changed. The BSR definitely changed beyond 460 trollins of difference, or 50% intraocular difference. So if you ask me what's the take home from this 10 minutes presentation, yes, retinal illuminance and the BSR relationship, we need equiluminance target or equal retinal illuminance in both the eye to summate any information better, especially flicker information better. So I would end this talk by showing the first slide. As I said, this is going to prevail the most fascinating questions of all time, simply just by saying that science and nature cannot be fully explored at all. Thank you. I would also extend my thanks to my labbies and especially my mentors from LV Prasad Eye Institute, Shrikant and Amit Rugvedi Hatigalikar. Thank you so much for the opportunity.